Um, Also, assignment 3 can become a pit of despair for people that take late tokens. So be really careful about taking late tokens on assignment 3, because what happens is people take late tokens and say, I'll just take an extra day or two to do the allocator problem. But then the issue is there's no TA office hours. And then you're kind of stuck debugging stuff on your own, and that's problematic. And so just try really hard to start early, get the work going, and get through all your challenges. Follow the outline that I give in the assignment, because that'll help you build it incrementally without running into all kinds of trouble. And just try really hard to not leave anything past the due date if you possibly can, because usually what happens is students send me their code and I try to help them debug it, but then I'm busy with a lot of things as well. So, just be really careful with assignment 3 and taking late tokens and then requiring TA help, because that becomes really problematic. It becomes a little bit challenging. Okay, just if it happens, but just try to avoid it. Okay. All right. Well, I do want to get started. This happens to be yet another busy lecture, but hopefully we'll get to it. There's a really fun thing at the end, and I want to make sure we have time to talk about it. But remember that last time we started talking about allocators. How do we build a facility so that we can manage a large memory pool so that we can start doing things like making exciting data structures and having values that last longer than a function invocation and so forth? Okay, so we talked about explicit allocators, or we introduced them at least, where the program is responsible for saying when it's done with memory. So that's the big issue with explicit allocators. They must explicitly release memory. And remember that we had these issues we had to think about. Fragmentation, the fact that we may have a total amount of memory that's available, but it's scattered amongst a whole bunch of little fragments, and we can't coalesce those free spaces, because once we hand over a chunk of memory, we can't really move it around anymore, because the program may have pointers into it, pointers out of it. We can't go and adjust things. Okay, and then we talked about data alignment as well, and alignment is going to actually make an appearance again. So if you have any questions, we can talk about it, but just be aware that alignment is another thing that the allocator has to think about. Not our allocator. Like in assignment 3, you don't have to think about allocation and alignment. But in the real world, you have to think about it quite a bit. Okay, so we had these functions that we talked about, and realloc as well, which I talked about. Remember that malloc, you say, I'd like a chunk of memory, whatever size, and then it tries to give you back a pointer to a chunk of memory that is at least that size. Okay? Now you know the reason why it's at least that size, because it may try to align it. Okay? Then free, we take the pointer to the chunk of memory that we were using, we give it back to the allocator, and the allocator takes it back. Okay? And then you have realloc as well, which is kind of fun, but we're not going to talk about it. The only thing I'll mention about realloc is that it's a really powerful tool when you have a chunk of memory and you need to increase its size or decrease its size for some reason. So building growable, shrinkable data structures, which you already saw in like the first assignment, I think, building growable, shrinkable data structures is really facilitated by using realloc. Okay? But that's all I'm going to say about that right now. Here is a very common way of representing blocks of memory in our heap. So again, we have this pool of memory, and somehow we have to build structure into it. And so we might have chunks of memory represented with a layout like this. Okay? We have a header. The header says, how large is this chunk of memory? And then you have a question of whether or not it's allocated. So is it available, or is it in use by someone? Okay. Feel free to just find here. There's tons of seats in the front row. If you don't like the front row, there's plenty of other seats interspersed. Most of the students don't bite, so you'll be okay. Now, one of the interesting things is that if we have aligned blocks, so we want to make sure that we satisfy some data alignment properties, then the start of our header and the start of our payload probably will have some low bits that are always 0. Okay, like if we're aligned on 8-byte boundaries, then the bottom 3 bits are always going to be 0, which is interesting because we could actually use those bits to store additional information if we wanted to. Okay? Not the one that we give back to the user, because they don't want to know about that stuff. But we might be able to actually take advantage of that. Okay. Now, the payload itself, so that's the part that the program uses. Okay. So you look at the green area. That green area is the size that is what the user requested. Okay, that's the part that they're going to be playing with. We don't want to know what they're doing in it, and we want them to leave alone our parts of the memory block. And then we have padding at the end, which is whatever fix-up is necessary to bring this out to an aligned address. Okay, so this is the idea about how we can manage our memory in our memory pool. Okay. Now, a program requests memory. You may. Oh yeah, question. Yes, in general, the header is always going to be a constant size. Because guess what? It's going to be a data structure. It's going to be like a struct. You're going to have junk in the struct saying this describes the memory block. And so you're always going to know the size of that struct. And so it's neat because you can actually say there's always this sort of like n bytes at the beginning of my memory blocks that I know as header. Okay? And that's actually going to become really important because, like I'm saying on the slide, if somebody requests a chunk of memory, the allocator has to go look at the pool and figure out, well, what chunk can I hand back? Like, what piece of memory will satisfy this request? So, just a second, I'll get to your question. So the allocator is working with blocks that start with headers, and it knows how large they are. Okay? And so it goes through and finds something that is the right size, and then what it does is it returns to the caller a pointer to the payload. So it adds the header size. This is why it's nice to know that it's always a constant size. We add a offset to the header pointer, and now we have a pointer to the payload, and that's what we hand back to the caller. And then they can muck around in the payload as much as they want. Okay? Was there a question? Okay, great. So any other questions about this? So this is the idea. It's a pretty powerful idea. The caller doesn't care how the allocator manages the heap, and as long as the caller is responsible and stays within the payload, we're all good, right? Maybe you've seen situations, in fact, it's a constant circumstance that happens in assignment 3. You'll see people say, you know, I'm writing my allocator, I'm debugging my allocator, and I run the test program you give me, and it crashes inside of malloc. Now, not in your allocator code, but in malloc, the C standard library allocator code. And they say, is there a bug inside malloc? No, sadly no. What it is that somebody, your allocator in fact, has trampled on malloc's header, or it's gone past the end and trampled on the header of the next block. And now the allocator's confused, and it crashes. Okay, so this is a risky trade-off here that we have, that you're giving out a pointer to the payload and hoping that the program will not, you know, go outside of that region. Okay, so you can see how bugs can really interfere with this. Okay, so this is what I'm talking about right now. What can happen if a program accidentally writes outside of the payload region? If your allocator, you write your allocator, myalloc, myfree, and you run the test program, and you see crashes in malloc or you see crashes in free, your first thought should be, I am somehow exceeding the bounds of my pool. Okay? There's nothing to be ashamed of. It's just something to fix. I've caused malloc to crash many times myself in my many years of programming. Okay? It happens. So yeah, in these cases, the heap becomes corrupted. And I mean, this is sort of the challenge that you run into with writing these kinds of systems, is that you are doing management of memory and you don't have any programming language facilities to keep you from doing something horrible. That's kind of the problem. It's the exact same issue you run into with file system data structures. Okay? You don't have all the tools that we normally love to have in a language like Java or Python or anything like that keeps you from doing dumb things. Okay? So, you know, you're allowed to do whatever dumb things you want in C, and you can run into these kinds of issues. Okay, so any questions about that? It's always, I should have a question in the survey, like, did you run into any exciting or frightening bugs? Because that's always, you know, there's always fun stories that people have about bugs in these kinds of systems. Okay, when the program frees memory, what pointer is the program going to pass to free? It's going to be the payload pointer, right? Everybody got that? So we're going to get back a pointer to the start of the payload. And so what the allocator needs to do is take that pointer and turn it back into a pointer to the entire block. Now, how does it do that? Well, fortunately, we have pointer arithmetic in C, fortunately or unfortunately, depending on your perspective and what time of day it is. And so we just take that pointer and subtract the size of the header, and now we have a pointer to the header. And so we can just access the contents of the header through that pointer. Okay? And typically, marking this as now available is really easy, because if you have a separate flag or you have some state that says this block is now available, you just go set that in the header, and now the pool can pass that block back to some other request. Okay? So it's a pretty straightforward mechanism. The devil is always in the details. The challenge is getting all the bugs worked out of it, of course. Okay, now we could say that the heap, remember that we start out with this single pool, and one of the things that we haven't really talked about is what happens when somebody requests a chunk of memory and we have a way larger chunk than they need. Do we just give them back the whole chunk? Well, no, that's kind of a waste. We'd like to be a little bit more careful about that. So a lot of times what you'll see is you'll take the chunk and you'll chop it into two pieces. Okay, so that you end up with a header and a payload and padding, and then you get another header and a payload and a pad. Okay? But each header says how large the block is, and so that you can see that in the pool you'll end up with these contiguous blocks, so one is adjacent to the next, and you can use the sizes to get to the next block very easily. Okay? And each block says whether it's in use or whether it's available, and so they form an implicit free list. That's what we mean when we say an implicit free list. We can walk through the sequence of blocks and look at the status of each one. Are you free? If so, what's your size? Is that large enough to satisfy the request, and so forth. Okay? So the allocator has to walk through this sequence. Now, there are a number of strategies. Like we were talking before class started. There's first fit, which means we just start at the beginning of the pool and walk until we find a block that happens to be the appropriate size. And when we find one, we see, do we have to split it? Do we not have to split it? But we just, first thing that works, we just hand that back. Okay? Then you have next fit, which is identical to first fit, except we remember where we stopped looking. Because presumably, wherever we stopped looking is going to be a pretty good place to start again. And we may have to wrap around the end of the pool, come back to the beginning. So it's a little bit trickier logic-wise. But if you have a program that's doing a lot of allocations the same size, this can be a really good strategy. Because if you had an allocation, you had to search through the pool just to find a block the right size, and then you get another allocation of the same size, might as well just resume searching from where you were. Right? Okay, so that's next fit. And then you have best fit, which clearly is the best, right? Why wouldn't it be? So best fit hunts through all of the blocks and tries to find the smallest block that is large enough to accommodate the request. Okay? Now that may still need splitting because, think about your pool initially. You're going to have one giant free block, right? And so your first allocation request comes in. You've got 2 megabytes in your pool. Your 16-byte request comes in, and you think, okay, best fit, I've got one block. But you don't want to hand the whole thing back, so now you have to chop it into 2 pieces and hand back a smaller chunk. And then you have a smaller free block, right? Any questions? So this makes sense? All right. When we free a block, we would like to coalesce it, because remember, we don't want to have a dumb allocator. Now, one of the things that I recommend in the assignment is don't coalesce right away. There are plenty of pitfalls when you try to coalesce blocks. So initially, when you're writing your allocator, you could just ignore coalescing. But then remember we have the problem of false fragmentation. We think memory's fragmented, but it really isn't. We're just dumb, and whoever calls our allocator is going to be sad because they won't be able to get their allocation request satisfied. Okay, so we may have a situation. In this case, we're freeing the 71-byte block. You can see that who cares about alignment, right? I just chose a bunch of random numbers. But anyway, we have the 71-byte block that we are freeing. And in this case, it's really easy to figure out what is the next block and is it available. Okay? because I just add 71 bytes or whatever the size of the block is. I get to the next block header and I say, are you free? And it says, yes, I am. And you say, okay, great. And all you really have to do to coalesce these is just change the first block's size to include the second block. You don't have to touch anything in the second block, and you can see now this is why when you malloc things and you get back a chunk of memory, sometimes it has fun little garbage values in it. Well, it's because the pool has things that it's doing in that memory. Okay, so all we really have to do is just say, hey, the 71 byte block, now it's a 127 byte block. And so that encompasses the next block. All right, make sense? Yes, this is easy, right? We love this situation. Now, when you have a situation where you want to coalesce with the previous block, then that's a little bit more annoying. Okay? So how do we find the previous block if each block just says, this is my size? Okay? You don't know the previous block's size. So this is a bit of an issue. Okay? So one option is to run through the entire thing. I mean, if you're doing this on a continual basis, then when you release a block, well, what ones will you need to worry about coalescing? Well, just possibly with the one before it, possibly with the one after it. Those are the only blocks you might possibly need to coalesce with if you're continually coalescing as you go. Okay? So you could just run through. Now that's linear time, and if you're writing an allocator, you don't like linear time. You'd like it to be constant time. You'd like it to be really fast. Okay? So there is a simple solution, which is, why don't I just replicate the header at the end of the block as well? We'll call it a footer, but really it's just another header at the end. Okay? And so since you have a header at each end, well, if you're at you're at a block, you're pointing to the header, well, all you need to do to see the previous block is subtract another, size of your header, and you'll get to the previous block's struct. And you can say, hey, what size are you? Are you free? And then it becomes really easy. And so that would be a constant time coalescing mechanism with the previous block as well as the next block. Okay? Constant time, constant number of steps. We love it. Win, right? Profit. We're the best. Okay? This is, again, the assignment will describe all the things. It's not too difficult to do this, especially if you pursue the approach that's described in the assignment and just say, I'm just going to use an int for size. I'm limited to 2 gig allocations. Well, the test program definitely doesn't get that big. But, and then positive or negative just indicates whether or not it's available or in use. If you do something like that, then you can put an int at both ends. And then you can do boundary tags and do constant time coalescing. Okay? It's up to you. Now, the implicit free list is nice. And you can code it up really fast, and it'll work. But when you're allocating memory chunks, now you have to look through the entire pool. And this is a bit of a drag, because if you think about it, we already know there's no point in looking at an allocated block. Like, can I use this block? No, it's allocated. Somebody else is using it. Okay? So why would I even look at allocated blocks? So here are some interesting observations. We really only care about the free blocks. Those are the ones that are candidates for satisfying allocation requests, right? Why would we even look at the allocated blocks? Here's the other observation. If the program is written properly, it shouldn't be using the space in our free blocks, so we could use it to put other information in there. And so you could use that, for example, to chain the free blocks together in our memory pool. And that way, when an allocation request comes through, we can just search through our free list. Okay? And so, yeah, just as an example, you have a linked list built in the free blocks that chains them all together. Okay? So this is called an explicit free list approach. Okay? So you'll see on the assignment that it talks about, you could implement an implicit free list or you could implement an explicit free list. An explicit free list uses the free blocks, uses a little bit of extra space in there to say, here's a pointer to the next free block. Okay? So you can see now that the headers might change depending on whether or not it's a available block or an in-use block. Okay? Does it make sense? No questions? Cool beans. Now, how do we actually manage or structure these blocks? That's another question that we could ask. And honestly, if you happen to be a systems person, then this may be more interesting to you, but I don't actually find this particularly exciting. But there are many strategies for organizing the available space in an allocator. In fact, if you go on to take CS 124 and study operating systems, we'll talk about a whole bunch of interesting ways that people have chosen. I almost always have a problem on the CS 24 midterm about some alternate way of managing memory as well. There's a lot of strategies, and it's pretty interesting. So here's just a few examples that I'm not very excited about, so I'm going to kind of skip over them to the more interesting one. But you could say, well, the free list will be in last in, first out order. That's really fast because you just put the available block on the front of the free list. That's always constant time. That's super fast. Okay. So, and then that talks about, what the implications of that may be. Here's another example. We could keep our free list in address order. That obviously would be a little bit more complicated because when we free a block, we have to hunt through the free list and make sure we hook things up properly. Kind of a drag. Okay. So, what are the implications of these approaches? I kind of don't care, and that's what I was saying. Like, if you were doing systems research, you might take programs like Postgres or GCC, and you might run them and watch their allocation requests and their free requests, and you might run them in a simulator to see how the system would behave if you had one allocation strategy or another allocation strategy, and it's just like, okay, that's great, but somebody else can do that, because I don't find that very interesting. Here's a more interesting one. In fact, you see this a lot in most sort of standard library allocators, is that they'll do something where they group free blocks based on their size. This is a fantastic approach. Most good allocators will do something like this. And so this is an example called segregated fits, where basically you have multiple free lists, and each free list only contains blocks that are within a particular size range. So just as a silly illustration, you can see that I have here 1 kilobyte sizes. So 0 to 1 kilobyte might be one group. 1 to 2 kilobytes would be another group, and so forth. Okay? And so you can trust that if you need, like, somebody comes in and says, I need, like, really badly, I need 2,080 bytes. Okay? Then you just go and look at the size class that you know will fit that. And you don't even look at the smaller blocks. You see how powerful that is? So this is a really nice thing, is that now I can know, okay, these are the blocks that I have available that might satisfy the allocation request, and I don't have to even look through other things. Okay? So when you allocate memory, yeah, you have a first fit strategy, but you start with the appropriate size class. So yes, it's first fit, but we're already starting with the appropriate size class, so it's kind of actually best fit. We're already looking at the best candidates for what blocks might satisfy this request. Okay? And so if no block is found, you go to the next larger size class. So let's say that you get the 2080 byte request, and there's nothing in there, so now you go to the 3 to 4 kilobyte, and then maybe from there it starts going 4 to 6, 6 to 8, 8 to 10. You find a block. You may have to break it into pieces, and then you can put the available part into the appropriate size class. Okay? So this is a really powerful approach, and so that's why most operating systems actually do something like this in their standard allocators used by applications. Okay? When you free memory, well, you can coalesce if you need to, and then whatever you end up with, you put that into the appropriate size class again. Okay? So this is really cool. There's a whole bunch of other things you can do, other techniques you can use that make this even better and make your allocator even more sort of resistant or resilient against fragmentation. Okay? I'm going to talk about that momentarily, but I don't want to get too caught up in it. It's an exciting topic, but that's why I don't care about the strategies on the previous slide, because like nobody really wants to use them unless you want to just write a really simple allocator. Okay? Yes? How are the size classes determined? They're usually hard-coded into the program. So you might have power of 2 size classes, or you might even have like some allocators will have zones, and then each zone will be dedicated to size class ranges. So like you might have a zone where it's like, I'm going to handle 32 bytes all the way up to 1,024 bytes. And then you might have another zone with 1,024 bytes all the way up to 64K bytes. And so the idea is within each of those zones you may have multiple free lists, but you know that it's a fixed range of them. Okay? And how do you know what to choose? Because if we're saying that this is hard-coded in the allocator, well, like I said, somebody will run a bunch of programs and see how the allocator behaves and say, this was a good choice, or they'll say, this was a bad choice, we need to tune it better. So there's a lot, this is one of the things about systems is that you'll notice there's not like theoretical underpinnings necessarily for all the approaches and choices we make. Sometimes it's just, in practice, this is what worked best. Okay? Yeah?
If you kept each free list sorted by ascending size, wouldn't it have the efficiency of best fit?
If you keep free lists sorted by size, would it be equivalent to best fit? Yes, I believe it would be. Yeah. Just the only problem then is the deallocation overhead. You have the bookkeeping overhead of deallocation to worry about. And the thing that you have to always think about is like, okay, so the block that I have, I'm freeing, and it'd be easy enough to do an insertion sort. Everybody I think knows how to do that. But then you coalesce, and so you have to go, if you coalesce, and you have to pull those things out of the free list and then, put the new block in. And so it just sort of adds up a little bit. Okay. All right, I'm going to hurtle on because we do have a lot of other interesting things to talk about today. So yay heaps, right? That allows us to write some really interesting programs, some powerful programs that can, do interesting computations and allocate memory proportional to the inputs in some way, okay? But heap management is a hard problem to solve. Now, it's not impossible, right? If a whole bunch of CS24 students can do it every single year, then it's not impossible. It just takes a little bit of effort, right? But we don't want to make every program solve this problem. And so what we do is we build this as a library and then let applications use it. Okay? That's the idea behind having an allocation facility. So this is part of the C runtime. Okay? So heaps are important to understand. Let me just explain a few details. Again, this always crops up. Think about the overhead. Okay, I've got my block. It's got a header. It may have a footer as well if I want constant time coalescing. I've got a payload, and I may have padding. So if I allocate a whole bunch of little tiny objects, every one of those blocks that was requested is going to have a header, and it may have a footer, and it's going to have a padding. So I'm losing a ton of space for each one of these allocations. That's a drag. Okay? And then think about when I allocate, I've got to hunt and find a block and probably cut it in pieces. And when I free, I've got to release that block and probably coalesce. So you've got a lot of overhead in your memory heap just for bookkeeping. You have both time and space overhead. Everybody see that? That's a big deal. And so a lot of times people will have alternate strategies for doing a lot of small object allocations. Okay. Also, fragmentation. I've been talking about fragmentation. When do we actually need to worry about fragmentation? Here's the thing. There's like a recipe for fragmentation, and if both ingredients aren't there, you don't have to worry about fragmentation. Fragmentation occurs when you have a combination of varying size allocations and varying lifetimes of those allocations. Okay? Those two ingredients have to be there to get fragmentation. If you think about it, if I have a whole bunch of different allocation sizes, but then what happens is I do all those allocations, and then I release them all, and then I do a whole bunch of more random-sized allocations, am I ever going to have fragmentation? No, because when all of the things are released, they'll all be coalesced back into one happy giant pool, right? If I have a whole bunch of uniform size allocations, so everything is always 100 bytes, allocate, 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 and the different objects are different lifetimes. So I free this 100-byte thing, and then I want to allocate another 100-byte thing, and I free these 500-byte things, and then I allocate 2 more 100-byte things. Am I going to have fragmentation? No, because I'm always going to have blocks the appropriate size to satisfy subsequent requests. Right? So you can see that there's this combination of varying size allocations and varying lifetimes. The mix is what's deadly, right? Like ammonia in bleach. Scary. Okay, so code that always allocates and deallocates blocks of the same size won't have fragmentation. Code that allocates blocks of varying sizes, but they all have the same lifetime, also will probably not have fragmentation issues. Okay? So this is something important to think about, and this is like allocators have to be designed for the awful case because they don't really know what application is going to use them or how it's going to be used. Okay? Any questions? This stuff always makes an appearance on the midterm, so that's why I'm kind of belaboring it, because I want you to do well. Okay. All right, stacks, faster than heaps. So if you have a choice and it's a fixed size thing, it's a local variable or it's a struct and you just need it for some computations and then you're done with it at the end of the function, use the stack. Remember, the program is hard-coded to use the stack, so it'll be super fast. Okay? And now you understand why. Like, what's the overhead of saying I need this data structure on the stack? Add some amount to the stack pointer, right? Add a constant to the stack pointer. That's really slow, right? That's super fast. Heaps have a different set of capabilities, but you can see how allocating a block might involve a lot of work. So that's a lot of overhead. And so that's why we prefer to use the stack if we possibly can, but if you can't avoid it, you want to do something fancy, then the heap is available for use. Okay? Make sense? Alrighty. So we're going to start changing subjects a little bit because we're going to set up for the next week. I'm so excited. I feel really bad for all the pre-frost that came this week because next week is actually the really cool week in this class and you're missing it. Come back. Come back as a student and take CS24 and then you'll be stuck with it. So anyway, there's two major optimization principles that you see over and over again in systems. Okay? The first one is make the common case fast. Okay? So you look at programs, you look at what they do. Most frequently, all programs have certain common behavioral patterns, and you try to optimize the computing hardware to make those cases fast. Okay? So that's pretty obvious. Make the common case fast. We'll talk about that a lot in the next half of the class. Then you also have the other principle, which is make the fast case common. Because you're always going to see that compute hardware is good at certain things. And so if it's good at some things and bad at other things, let's arrange our computations to take advantage of the things it's good at. Okay? So these are the two optimization principles, and we'll see them over and over again. Make the common case fast, make the fast case common. Okay? A really simple example is we've talked about, do you want to store your local variables on the stack, or do we want to store them in registers? Do we want to pass arguments in registers? Do we want to pass them on the stack? Well, which one of those is faster? Yeah, registers are way faster for all kinds of reasons we'll talk about in a few weeks. And so, if that's the case, let's apply the second optimization principle of make the fast case common. We'll pass all of our arguments in registers. We'll use registers for local variables. We'll use registers as much as we can because then we know our program will be fast. Okay? So that's a simple example. Data alignment. Make the fast case common. Remember, when we access memory, we're on a 64-bit processor. So I read memory in 8-byte chunks, and the 8-byte chunks are aligned on 8-byte boundaries. Big shock, but that's how the hardware is designed. So the compiler will adjust your program, whether you know this or not, it does it, to use memory as efficiently as possible. Okay? We want to try to avoid having two accesses to read or write a value. So this is what GCC does. It follows a really simple rule. You have a data value of some size. It just makes sure to align that thing so that whatever address it starts at is evenly divisible by the size. That's all it does. Okay? So here's some simple examples. A char is 1 byte, so that's easy. I can always make sure that it's on an address that modulo 1 is 0, right? That's math that even Donnie can do. Int 4 bytes, so it just makes sure to put that at an address that starts at some value, modulo 4 is 0. Okay? Longs are on 8-byte boundaries, and pointers are on 8-byte boundaries as well. Okay? Everybody got it? If we do this, then we can guarantee that when I read or write any of these values, it will always only require one memory access. It won't span multiple memory cells. Okay? Now, we've all used structs. You've seen them already. I'm hopeful that you're comfortable with them because you're going to be seeing a lot more of them in the next couple of weeks. But data alignment is actually really central in how structs are laid out. Okay? So we have struct members that are different types if we want. Each member has its own unique name so that we can reference them in our programs, and the members can be whatever we want. Okay? So here would be a linked list because we just can't get enough linked lists, right? So we have a number, which is an int. Remember, ints are 4 bytes in x86-64 on Unix variants. We have a string pointer, and we have a node pointer. So those are both 8 bytes. So if we did something like this, we said struct node n, and then we initialize its various values. Basically, so I already talked about this. The compiler has to figure out how to lay this struct out in memory. There's a rule that C specifies that when you have struct members, they always have to have increasing addresses in the order that they're specified. So number first, string next, next last, and so each one has to have, you know, a higher address. And so we could lay it out like I have on the slide. You know, so this takes up 20 bytes. And we have it laid out like this. You can see number first is 4 bytes, and then we have 2 pointers. What's bad about this approach? Hopefully obvious, right? I can read the int, no problem. That's always going to be one read or write. But reading the pointer, well, now it's crossing 8-byte boundaries. And so to read each of these pointers, I'm going to have to do 2 memory accesses and reassemble it on the processor. Okay? Thankfully, we don't have to think about this, but if it's slower, why not avoid it? Okay? So this is the issue that we run into. Accesses to string and next become 2 reads instead of just 1 read. Okay? So shockingly, we actually have doubled the cost of accessing our data structure. Now, it's a little tiny amount, and double that is still a little tiny amount, but this accumulates over time, and so you have a computation that can be very slow because of all these little wastes. We'd like to not lose that space. Now, if you have other values that either precede or follow this struct, now their alignment is messed up too. That doesn't sound good at all. So we need to find a better way of laying these things out. Okay? So the compiler will go in and just add a little bit of extra space. That's all it needs to do. Okay? And so in this case, remember the rule that I said before. GCC will always make sure that values are laid out such that their starting address modulo their size is 0. If you follow that rule, you automatically get the appropriate padding added to your data structure. Okay? So string and next are 8-byte values, so they should be aligned to start on 8-byte boundaries, so we just shove in 4 bytes of extra padding. Okay? And now, when we access these things, we always get a 1 read or a 1 write access. How cool is that? Okay, any questions? Somebody always asks, can you access that padding? Can you store stuff in it? Can you read stuff out of it? Yes, if you're naughty with your pointers, you can totally do it. I wouldn't recommend it, but one certainly could. In fact, it's pretty straightforward because you can actually, everybody's familiar with size of, because we've seen that before, but there's another operation called offset of, which is also a compile time sort of, I don't know if macro is the right term, but it's a compile time function. It will tell you the starting offset of a member of a struct, and you can use that to figure out what parts of your structs are padding and what parts aren't. Why would you do that? I don't know. It seems silly to me, but one could. Okay? A well-written program should never touch the padding. That's kind of the way it should be. Okay, so the compiler is going to figure out these details, and it'll have a table. Like, it'll say, node is a type, and it'll have this table saying this is where each of the members start, and here's their types, and here's how large they are. Okay, so it'll do all of that. Okay, and so when you have C code that accesses the struct members, it uses that table to look up how to generate the assembly code. Crap, we have to think about assembly code again, right? I know we're all thinking that. Because I thought we were in allocator land. We don't have to think about assembly code anymore. So if we get a pointer, where is n going to be? We talked about this already, like a whole bunch. RDI is going to be holding the node star when we get into that function, right? Everybody with me? So then we can use our all kinds of fancy pants indirect memory access operations to access the members of this struct. How cool is that? Okay, so we want to store 42 into n arrow number. So we just say, hey, store the value. It's a 32-bit value, so move L, and store it where RDI points. Okay, that was easy enough. Then we want to store answer, which remember is a string constant, so it'll be somewhere else in our program. We'll have a pointer to it. And so we do move q lc0 into, starting at 8 from RDI, we'll just store 8 bytes there. And then the same thing with n arrow next is null. Well, that's just 0, so we'll store 0 in the next 8 bytes that starts at offset 16. Everybody got it? So easy, right? Now we can access, like, our powers are growing. We can do all this cool stuff. Okay, so here's another example. How fun is this? This is what GCC will do to lay this out. Int I, char ch, int j. The largest thing is 4 bytes. So it just needs to make sure that everything starts on a 4-byte boundary. Okay. So it's going to pad ch with 3 additional bytes. All right? Hopefully nobody is shocked by this. Hopefully I have no bugs. But here's the other thing that you can see. When you say rec arrow ch equals a, again, this is a great example where there are no types at the assembly code level. It's just tell the machine what to do that corresponds with what the high-level language says. So if I say store a, well, 97 is the value of lowercase a in the US ASCII character set, and I think that's been carried forward into UTF-8 and so forth. So, but anyway, we store 97 into 1 byte, so you can see move b, the byte that's at RDI plus 4. Okay, that's how this is done. So you can see there's no types at this level, which is what makes it so exciting. Yes?
This works really great on little Indian systems. Does the compiler have to worry about weird offsets on big Indian systems?
You know what? It has been decades since I've used a big Endian system, so I can't answer that question. Yeah, sorry. I don't even know what system I would go tinker with if I needed a big Endian system to play with. It's been years.
Would you have to move the char at offset 7?
It may be that the char would be stored at offset 7, but I don't know. I just don't know. Probably not, it would be my guess, because it's nice that these things are all just sort of left justified in the data structure layout, but I just don't know. I don't know. Big Endian, what's that, right? I think the last one was a Spark station. I think it had a Motorola processor. But that was years ago. That was several decades ago, so I don't even remember. Okay, so size of S1 reports 12 bytes. Now, you can pack these things if you're crazy. You can actually say, I'd like this data structure to be packed into as small a space as possible. This is a non-standard GCC extension, and if you do this, you'll see that the generated code matches what you say. And if you were to ask what the size of this data structure is, now it'll say 9 bytes. Okay? But you can see that this can get really nasty, because if you have, for example, an array of these things, then you're just going to have a whole bunch of non-aligned accesses. Okay? Now, if you have this and then you have another local variable, then GCC will probably pad out the struct so that the local variable is aligned, because it's why punish you all over the place? But if you have arrays of these things, then you're going to have a lot of non-aligned accesses. Okay, so this is useful in I/O situations where you want to save bytes, but in general, we will not do this. Okay. All right, yeah, so if you have a small member at the end of the structure, what happens? Okay. Well, the compiler is still going to pad based on the size of the largest member, because it's thinking about what if you have an array of these things. Okay? So you can sort of see that compilers have a lot of things that they think about very carefully. There's a lot of alignment issues that they consider when they lay out these data structures, and correspondingly, as a human being designing a data structure, you can definitely make choices that make your structures larger or smaller, and can have all kinds of consequences that you may not realize if you don't know what the compiler is doing. Okay? So that's kind of an interesting little issue. I remember very distinctly that when I was at Microsoft for my first full-time job, that one of the guys said, I'm going to go design the data structure that we're going to use in our system, and he spent a week designing it. And I was like, oh, how very interesting. And he was thinking about all these kinds of issues because we were writing it in C++. But this is the kind of thing people don't think about so much anymore. So it's kind of become a lost art of figuring out how to lay out data structures in memory efficiently. Okay, any questions about this? Yeah, okay, so, oh yeah, this happens with code as well. That's all I'm going to tell you here. You can read about that later, but if you were to compile at an appropriate optimization level, it actually will lay things out so that code is also accessed efficiently. That's all I'm going to say here, because I want to just keep going. So computers are fast when we access things aligned. We only need one access, so why don't we just make that the common case? And so that's an example of an optimization principle we'll be seeing over and over again in this class. Okay? It does waste space, but the funny thing is that more space is always easier to come by than more time. Seems to be a truth about life. You can always throw more space at things. That just requires money, but more time tends to not be as easy to come by. Okay? All right, questions? Who knows about unions? Who's used unions before? Okay, a few of you. Unions are a weird data structure. I'm going to mention them very briefly because you will run into these. In fact, you'll probably see them on assignment 4. A union is a special kind of data structure where all the things overlap. Remember that before we had the offsets chosen so that they wouldn't overlap. That seems reasonable in a programming language design. But you can also create unions where it basically has all of these different fields, but they all occupy the same space. This allows you to use it for one thing or another thing depending on the circumstance. Okay? So the reason why you might want to do this is if you have a situation where you have a value but you don't know what type it might be, and you want to support the possibility of storing many different kinds of things in that one variable. Okay? So I'm going to just show you this really quickly so that you can look at it, but I don't want to spend too much time on it. A lot of times the way these unions are used is they'll be preceded by something that says what it is. So you have like a val type that says this is an int, or this is a string, or this is a float. Okay? So that you know how to interpret the union. If you didn't know how to interpret the union, you're SOL, as they say. Right? You have no idea how to interpret that value. It could be a really large int, or it could be a pointer. Or it could be a float. You know, you have no idea. There's no way to tell from the value itself. So you would have code like this, where you look at the type. Well, depending on the type of the thing, then you go ahead and access the member of the union that will give you the right understanding of it. Everybody got that? A little crazy, but it's something people can do. All right. Last thing, we're going to spend the last 6 or 7 minutes talking about this, that C, being a relatively low-level language, you can see that it's pretty straightforward to translate all of our facilities and capabilities into assembly code. You do not have to write your allocator in assembly code, but the cool thing is that now that you know how to translate C code into assembly, you could if you were nuts, right? You totally could. But you don't need to, thankfully, because we have C to do that. Okay? But this is all pretty straightforward, but there aren't a lot of runtime facilities. And so you start running into frightening situations. I have an array of 4 ints, and I decide to access the element at index 4, which should not exist, right? Because the elements are at indexes 0 through 3. I can also say r minus 1 and read or write it. Well, what is that going to do? Probably not crash if this is a local variable. Probably not crash if it's allocated on the heap. A little scary. Okay. Maybe it'll affect another local variable if they're on the stack or if they're next adjacent in the heap. Right? We have no idea what's going to happen. It depends on the layout. But this is possible in C, and people look at this and they say, wow, that's really frightening. Especially because you can start getting into new and exciting ways for your program to misbehave. Okay? Like, let's say that you have a buffer, and you call the single worst function ever written in C, getS. GetS is banned from my classes, and it should be banned from your life. We should all pretend it never happened. But what getS does is it reads from standard input until it sees a new line or end of stream. And it just writes the bytes that it reads into whatever buffer you pass it. Okay? That's all it does. So I'm getSing into my buffer of 100 bytes. Seems okay, right? Well, if I type 20 bytes, we're okay. What if I type 300 bytes? GetS doesn't have any way of indicating how large the buffer is that it's writing into. This is why it was a horrifying oversight in the design of the C standard library. Okay? Great example. Whoever wrote it probably will never admit it because it was a terrible idea. But there's another version called fgetS where you get to say this is the size of the buffer I'm writing into. And that way it will stop when it hits the end of the buffer. Okay? Once you start having buffer overflows, now you get to start having fun with other people's programs. That's always where it starts to get exciting because now we can start leveraging these things to compromise security. There was a fun one that we would do when we were undergrads, but OSs weren't written as well. You could send a ping of death to somebody's computer. They'd be working on their homework or playing computer games, and all of a sudden their Windows machine blue screens. Okay? The way that you would do it was send them a packet in pieces that assembled to larger than 64 kilobytes, because that was the maximum size of a packet. And like your computer's like, hee hee hee, and you send the packet pieces, and their computer tries to assemble it into a buffer that's no larger than 64K, and it overwrites something else and causes the computer to crash. Okay, that was fun. Okay. Thankfully, they don't do that anymore. What if we had code like this, where we have some buffer that we receive a request in, and we have an authorized value that says whether or not they're authorized to do the thing that we want to do. Okay? Well, you have to think about how is this laid out on the stack. This is one possible layout. Now, in all likelihood, authorized would be in a register, which is way safer than putting it on the stack. But if we had a situation like this, where the buffer is laid out in memory, and then authorize is after it, in other words, above it on the stack, and somebody tries to overflow the input buffer, then maybe they can plant a value in authorize, and now they can start making the program do things the original creator didn't intend. Everybody see that? So you can target values with buffer overflows. What's another value you could target? The return address. Right? If you target the return address, so you can see I've changed things up a little bit. I've moved authorize later so that maybe it won't be laid out badly. If you're writing software and you're trying to make it secure by rearranging variables, you're doing it wrong, okay? Just so you know. But we could try to hit this return address and make the program jump somewhere else and start executing something else. Now, where do we make it jump? And what do we have it execute? Well, this is the beauty of buffer overflow exploits. If I'm passing it a bunch of data and overflowing a buffer, why don't I just include the program I want it to execute in the buffer as well, right? That makes it a little bit easier. And so then you say, all right, but now I have a challenge of hitting that return address, getting the right value in there, and then making sure it jumps to the start of my code. Well, there's tricks. It's like so easy to make the target much larger. There's this thing called a no-op slide. x86 happens to have an instruction, hex 90. It's a no-op. When you run it, it does nothing, and it just goes on to the next instruction. So if you have like a megabyte of no-ops, then it'll just go all the way through them until it gets to the end of it, and then you have your code that you want to run. Now you have a 1 megabyte size target to put into the return address. And so you can start to design your exploit. So you can see that these kinds of things are really nasty. Buffer overflows are the largest cause of security exploits ever since people have started exploiting programs. Okay? Memory leaks. Okay, so that's another issue. You all are familiar with that. What I'm going to do is just skip over this. We're relying on the explicit allocator to do things properly, right? To say I'm done with this memory so that you can reuse it. Implicit allocators take that away from the application, take it away from the program having to do it. Okay? But what I want to do, since we're out of time, is I want to point out an issue. We have this cool language C, and I've been telling you all the way along that C was really revolutionary in its day because it opened up the potential to run a piece of source code and compile it to a whole bunch of different platforms. That was revolutionary for its time. The problem is it has no guardrails. And so it's really easy to write programs that have all these kinds of buggy behaviors that can be taken advantage of. And so what we're going to do is take another step up the abstraction hierarchy and start talking about approaches that mitigate or remove these issues. So what we're going to do next week, and this is why all of you pre-frost are going to be sad, because next week is awesome. We're going to talk about how to implement implicit allocators. You'll get to implement one for homework 4, and it's a really fun lab. I'm so thrilled with it. Object-oriented programming. How do we start building encapsulation and polymorphism into our data types? And then we'll talk about exception handling. How do we implement exception handling as well? So that's what we'll talk about next week. We'll see you then.